13, aqueous equilibria and acids and bases. This is our big acid-base chapter for Chem 152. We'll kind of fill in all the rest of the information about acids and base that a lot of the other classes didn't cover. So first we'll start off here with acid-base theories, Arrhenius and Bronsted-Lowry theory, Lewis theory, acid-base strength, dissociation in water. So we're going to be bringing in like equilibrium concepts into the acid and base. I mean, that's really what we're focusing on here. So while we'll be talking about these other first issues, this part here at the end with equilibria and solutions of weak acids and weak bases, this is going to be a major point for us here. The major element that you'll be learning that's a little bit different from what you've seen in previous courses with acids and bases, right? That's the addendum, bringing in the concepts that we saw in the previous units on equilibria into this. And then relationship with Ka, Kb, that we'll learn about those as the equilibrium constants for acid-base dissociations, and then finally acid-base properties of salts. We're not going to cover the FYI, what is acid rain and its effects part, simply because there's a lot of content here in that. It's a little bit of flavor, it's interesting, but I'm not going to ask any questions about it. So key terms, so we'll be talking about the acid-base theories, right? So the Arrhenius theory, that's the simple theory where an acid is something that donates H plus to a solution and a base donates OH minus, simplest theory. In Bronsted-Lowry, which is typically our acid-base theory for water and other protic solvents like it, something transfers H plus and then a base is something that accepts it. And in Lewis theory, we say that an acid accepts a pair of electrons and the base donates it. This will be a little more complicated and we'll see it close to the end of this chapter. Conjugate acid-base pair, this will be another key point of review, a chemical species whose formula varies only by one proton, so they're like if we ran the reaction in reverse, who would become the acid, who would become the base. We'll see a little bit of that going on. Strong acids and strong bases, these are ones that dissociate completely, which makes them a strong electrolyte. I'm going to kind of step out of the way a little bit here so you can see that, but you'll also have the slides. So if I'm ever standing in front of something, please be aware that you can go back to the slides and if you can't see something. Weak acid and weak base, so these only partially dissociate in water, so they're a weak electrolyte, and they'll establish an equilibrium, and we'll see that going forward. pH, so our power of 10 expression of the H plus or H3O plus concentration. pH of a solution is the negative base 10 logarithm of the molar hydronium ion concentration. Again, it's the same pH you've seen potentially in an earlier chemistry class. Acid-base indicator, a substance that changes color in a specific pH range. And the Ka and Kb, much like what we saw before with the Kc and the Kp, these are equilibrium constants for the dissociation of weak acids and weak bases in water, or it'd be specified if it was in a different solvent. So typically we're just going to have everything in water. Percent dissociation, it's another way to measure the strength of an acid under particular circumstances, like how much of it dissolves under particular conditions compared to the initial concentration, how much of it actively dissociates and produces H plus or accepts H plus or produces OH minus, or however we want to measure that base strength. And a polyprotic acid is one that contains more than one dissociable proton, so it creates more than one proton in the solution. So there's a little review here of the different acid-base theories. First, with the Arrhenius acid-base theory, we see that a substance produces H plus in the solution, or a substance produces OH minus in a solution. And those are not necessary. It's not necessarily a bad way to think about things. It's the simplest way, but a lot of acids will follow this kind of theory, and a lot of bases will follow this kind of theory. And like I said, the Bronsted-Lowry theory is more expansive, so everything that's an Arrhenius acid or an Arrhenius base is still a Bronsted-Lowry acid or a Bronsted-Lowry base. And similarly with the Lewis system being even more expansive, everything that's a Bronsted-Lowry acid or Bronsted-Lowry base is still a Lewis acid or a Lewis base. All the theories kind of compound upon each other, with the simplest and most restrictive being the Arrhenius, and then the next one up being Bronsted-Lowry, and then finally Lewis. But we're focusing here on the Bronsted-Lowry theory because that one's most important for understanding acid-base chemistry in water in particular, but it also covers other protic solvents like alcohols and ammonia and other liquids that could carry out chemistry with the transfer of an acceptance of H plus. And that's part of what makes those solvents protic. They behave like water in that they can transfer and accept H plus, and we'll see a little more about that. So conjugate acid-base pair, important concept, right? So we've got this HA, some donor acid, okay, loses its proton to this B, and then this BH plus now has it accepted, and the acceptor is the conjugate base. It's over here on the right side to this acid, and then the base is here, and this is its conjugate acid. The conjugate is typically the one on the right side. That's typically how they think about it, because it's the one that would be in the reverse reaction. Notice that we've got this little equilibrium arrow sign, like we've seen in previous chapters where we establish an equilibrium, right? That might mean that these reactions might reverse. Some reactions, and we'll see this with strong ones, essentially go to completion, but then that just means they have a really high value of K. But many exist in an equilibrium, which means that there'll be some of both, and there'll be some HA still around, and some A minus around, and some B around, and some BH plus around, depending, and the proportion of that will determine the strength of that acid in this instance. So when water, we say that water accepts a proton. Protic solvents accept a proton. They can kind of carry it and mediate that proton. Bare protons are not very stable, so they typically want to hang out with some solvent molecule that helps carry them around, and that's what's going on here. So when an acid dissociates in water, it protonates the water. That's the term we use. It adds a proton to the water, and then it becomes the conjugate base. What's left over from the acid becomes the conjugate base. And water here acts as the Bronsted-Lowry base because it accepts the proton and now exists as this protonated form. In water, H3O plus is the active acid medium. So it's the thing that carries out and creates the acidity in the water itself, is the H3O plus. It's what makes the solution acidic. We'll see similarly that OH minus, the conjugate base for water, not the conjugate base for H3O plus, the conjugate base for water, carries out basic characteristics of a solution. So when we make a solution acidic or basic, our major effect is on the solvent itself. But also we can see here how we can break these up into pairs and identify these as pairs because there's only a transfer of a single proton. This is very important. There will be questions identifying conjugate acid-base pairs. They're easy questions if you know that only one proton can ever be transferred in that kind of pairing. So just as a note, make sure you remember that. So here we have a base, right? This is where the conjugate base of water, OH minus, forms, and how OH minus is what creates basicity in aqueous in water solutions. And here we have a Bronsted-Lowry base, which accepts the proton from water. So water here acts as an acid, and then NH4 plus is the conjugate acid of NH3, the base. So you can see how, like, it's not that the NH3 had any OH on itself, it just generates it by taking a proton from water. So this is a Bronsted-Lowry base, but it's not an Arrhenius base. Many Bronsted-Lowry bases, operate in this same kind of way, like they're able to take protons from things. And that's how they establish their basicity. That's the basic theory. Like I say, the hydronium ion, they say, can be thought of as a hydrate of a proton. The book goes on about this, and that it's possible to create some higher order hydrates as well with water, but these get more complicated, and whether they exist as discrete molecules is a question. The H3O plus certainly does, and so we keep that as a simple way to express it, but it's not like any one molecule of water stays as H3O plus. The proton kind of plays hopscotch. It jumps around through the water to different places and associates with different molecules at different times, because in water the protons can move around. They don't stay with any one particular molecule. This has been tested. So like if I take regular water, H2O, and I mix it with deuterated water with the heavier isotope of hydrogen, D2O, they don't stay separated. Like the D2O and the H2O don't stay separated. Instead, they create a lot of DHO. Like the protons between water molecules exchange continuously. It's a process that actually helps hold the water together and gives it a high boiling point. It's part of its hydrogen bonding. It causes this thing called the protic field. There's a whole description we'll talk a little more about later how water's amphotericity does this. But just to keep in mind that H3O plus is an expression of that, basically that hydrated proton associated with water. Okay, and again, we're identifying a conjugate acid and a conjugate base in this example. So NHNO2 is our acid. It donates a proton to water, the base, and this is how it really exists, right? But we could also identify it as an Arrhenius acid since it dissociates in water to produce H plus ions. It's donating H plus to the water, so it's this Arrhenius, but it's also accepting it into the water system with a Bronsted-Lowry description. So HNO2 is both a Bronsted-Lowry and an Arrhenius acid, and its conjugate base is NO2 minus. So keeping all that in mind. So let's talk about the strength of an acid or a base, right? So an acid's and a base's strength can be determined by how much this dissociation moves to completion. So an acid would be very strong if essentially all of it is converted to its conjugate base and protonated water to the H3O plus. So a stronger acid has a higher value. It moves more in the direction of the products than a weaker one does. And conversely, the stronger the acid is, the worse its conjugate base is. And that's what they describe down here. If you start with a stronger acid, you'll get a weaker conjugate base. And that makes sense because the relative ability of this reaction to reverse itself is based on the strength of this base. So if this base is terrible and not able to take protons back, then this reaction goes essentially to completion. Similarly, for a base, if a base is a stronger base, the conjugate acid is not very strong and cannot reverse the reaction. But if a base is not a very good base, then its reverse reaction predominates. Keeping all this in mind. We can also think about this in terms of electrolyte theory, how many ions the dissociation donates to the water and how that might affect its conductivity. These are all related concepts. So we say that a strong acid is one that is almost completely dissociated in water and is therefore a strong electrolyte, meaning a one-to-one relationship between the amount of the acid I add and the number of ions that I get. A completely linear and complete relationship, a total dissociation, a reaction that goes essentially to completion, or a reaction with a very high value for K. All of those are ways of saying the same thing. All of those are true at the same time. So they show here how a weak acid is one that's only partially dissociated, and they give us a little picture to help us understand this, right? If this is a strong acid, it's essentially complete, so there's no HA left. If it's a weak acid, then there's a good amount of HA left and a good amount of both. If it's a really weak acid, then it really doesn't do anything. So we actually now have a continuum all the way from like the strongest acids that dissociate completely when they're introduced to water, all the way to the weakest acids, which are basically not acids. They don't do anything, right? And these are all acids and bases in water, right? Some in other solutions, there may be ways to make things even stronger or maybe other things, but within the Bronsted-Lowry framework that this chapter is talking about, all strong acids have to dissociate in water. And there is an upper limit to the strength of an acid in water dictated by the strength of H3O plus itself. So keep that in mind. Like that associated proton caps the upper strength of how acidic water can be at a given temperature. So there can be scenarios where you can exceed that. That's where, if you may have heard from pop science, like superacids or other things like that, they involve getting around this limitation by no longer producing H3O plus. We'll talk a little more about that with like the Lewis acid-base theory. So relative strength of conjugate acid-base pairs. So the stronger the acid, the weaker its conjugate base. So things like HCl are strong acids and they have terrible conjugate bases, okay? And H2SO4 and its conjugate base, terrible bases. And nitrate ion, terrible base because it's in the strong acid group. And as you go down, right, you can see that here's H3O plus, right? So anything that's a strong acid is stronger than H3O plus, so it gets completely converted to H3O plus. That's another way to think about the same thing that we've been saying. There's just a number of different ways people word this or say this, but they all end up substantively equivalent to this same concept here. All these acids are stronger than H3O plus, so they get converted to it. They go down a chemical gradient, they lose energy, and they become H3O plus. And any weak acids are weaker than H3O plus, so they're not able to totally protonate it. And if they're very weak, then they're really not able to produce any H3O plus at all. It's kind of a percentage thing. Yeah, they're less than H3O plus, so they're not, there's a continuum. How close are they to H3O plus? How much are they able to protonate H3O plus? You know what I mean? Like, so that's a thought. Similarly, the strongest bases are more basic than OH minus, so they're able to be completely converted to OH minus in solution. Weaker bases are closer to the strength of OH minus and able to produce it to some extent. And then very weak bases essentially produce none. So predicting the direction of an acid-base reaction. Okay, so if we look at this reaction, we got to look at the relative strength of the acids and bases involved. So in this example A, we have sulfuric acid, H2SO4. That's a strong acid. But NH3 is a weak base. We're going to look at the list of acid bases in a little bit, so I'll help you out with that. But like for now, we know that NH3 is a weak base. H2SO4 is a strong acid. So that will predict that this reaction essentially goes to completion because of the strong acid, and the base is completely converted. So that's this one. Down here, it's a relative question. Which base is better? Okay, which base is going to be better? Which acid is going to be better? So this can't give up any more protons. SO4 2- can't give up any more protons. So it can't be the acid. So this is going to be the acid. The CO3- is going to be the acid, and that's what we see over here. But which one will be a better acid? Well, if we look back at the chart in the table, we could go back to it, but if we did, we would see that HSO4- is a better acid than HCO3- is, which tells us this reaction goes in reverse. Sometimes you'll have the stronger base and the stronger acid like not on the same side, like in these examples. In these examples, the better base and the better acid are on the same side, which will mean that direction controls. But if they're swapped, then it's going to be, is this base a better base than this one is an acid? And then you can do that comparison and still decide the direction, because the one with the better acid or base will control. But we don't have an example here, and I don't think you'll see examples that are quite that confusing. But just keep that in mind. The stronger thing, whether it's an acid or a base, will control the direction of the system. And that makes sense. So factors that affect acid-base strength. So we can think about this, right? We know from earlier chemistry classes that HF is a weak acid, but HCl, HBr, and HI are all strong acids. And this has to do with how strong this bond is, and in a lot of ways how ionic this bond is. When the bond has more covalent character and it's stronger in that way, it doesn't ionize in water and acts more like a normal molecule. Whereas HCl, HBr, and HI will all ionize in water because of this strong electronegativity difference and the weaker overlap between hydrogen and these bigger ions. This is another way to think about this. The variation in polarity is less important than the variation in bond strength, which decreases markedly from HF, which has really good overlap and good strong bonding, all the way down here it gets weaker. So these are all factors that could affect the strength. Generally, HI could be said to be stronger because it's easier for the proton to leave, to dissociate, compared to the other two, but they're all strong in water, so the only way I could tell them apart would be from some other context. So this gives us a way to rank them, right? Like HI would be the strongest of these acids because it has the weakest bond strength. But again, since HCl, HBr, and HI are all strong in water, they're all stronger than H3O+. All of them act similarly for that use case. Similarly here, if we affect the electronegativity of a system, right? If we can make this bond more polar in nature, that will also make something more acidic. So since like methane, CH4, these bonds are essentially all the same electronegativity, so we don't get any dissociation of their protons. But in NH3 we get a little bit of it, but really NH3 acts more like a base than it does like an acid still. But if we thought of it as an acid, that's how they're thinking about it here. HF of this series is the strongest acid. It's a stronger acid than water, but it's not a stronger acid than H3O+. Keep that in mind. That it's still a weak acid because it's weaker than H3O+. That's how we determine that an acid is weak, not that it's a stronger acid than water. I talk here a little bit about oxyacids too. These are ones that have oxygens associated into the formula and then typically hydrogens attached to those. In these examples, nitric acid is strong, sulfuric acid is strong. I'm going to have a strong list at some point I'll show you, but carbonic acid and chlorous acid are not strong. But you can see how they all have a similar structure with this O attached to this H directly, and these are the acidic protons, the ones that are attached directly to oxygen, not ones that are attached to other atoms. Typically in structures like this, hydrogens are attached to the oxygen, and those become the acidic protons. Again, we see that here as well, like HOI and HOBr and this. The more stable this ion that leaves becomes, if the hydrogen is able to leave, the more stable this is, the more of an acid it can be. Since this chlorine can help pull electrons from oxygen, the oxygen doesn't have to hold the negative charge when the hydrogen leaves, because when it leaves as a proton, it leaves as a plus ion. So the oxygen gets left with this negative charge in that process, and the chlorine helps pull that away so they can share it, and that helps make it more stable so that this is a more strong acid. That's another way to think about it, and I think it's the best way for this series of hypochlorous acids. And again, generally, as we add more oxygens to an oxyion, we get a stronger acid as well. So perchloric is stronger than chloric, although both of these are considered strong in water, chloric and perchloric. Perchloric is stronger by other ways of measuring that. So adding more oxygens tends to make things stronger. And then finally, the relative stability, that's what they were talking about here as well. Having more oxygens helps spread out the negative charge and gives us more resonance structures. There's more detail going on with that, but essentially there is a justification for that in terms of spreading out the charge. So dissociation of water, right? So in 14.1 we saw that water could act as an acid or a base. And so what would happen if we thought about like water reacting with itself, okay? Like one water molecule acts as an acid and one water molecule acts as a base. Well, this process is called the dissociation of water, and it's a property of a water solution, okay? Of water in a container. It just does this spontaneously, and it does this with a given constant. It ends up being about 1 by 10 to the minus 14 as a K constant for this reaction, because we could think about this as like a reaction with an equilibrium constant like we saw in the previous chapters. We can't include the water because it's a pure liquid, so we end up with this thing they call the ion product constant for water. We'll learn a little more about this term ion product constant later, but for now we'll just say that this is like any other equilibrium where you have a liquid on one side and ion products on the right side, and this equation defines this process. Now for different solvents, like ammonia does this too. It has a different value though for its constant, but it still does this same idea. All hydrogen bonding protic solvents with protons that can move around all do this to some extent, and this is a way to quantify that process, to imagine that we're having two water molecules where one acts as an acid, one acts as a base, and they exchange like this. This rate changes with temperature, so the hotter the water gets, the more it does this. So this constant Kw is like all other Ks, and it's dependent on temperature. Reminder to go back to previous chapters for review of this if this seems a little unfamiliar. So because we know that this is 1 by 10 to the minus 14, that's the value of the Kw at 25 degrees, we know that one OH minus and one H plus have to both be produced by this process. If we take the square root, we can get the value of that concentration at 25 degrees Celsius for this setup, which is 1 by 10 to the minus 7. And so in water with nothing added to it, it's pure water, the concentration of the H3O plus and OH minus are both 1 by 10 to the minus 7 molar at 25 degrees Celsius. Okay. They calculate that they get the molar mass of this, how many moles per liter of water there are, and they make this adjustment to conclude that the ratio of dissociated to undissociated is about 2 in 10 to the 9, so it's very small. But remember, it's not always the same molecules, like they're moving all around. Which ones are ionized at any one time changes at random, and it's a constant motion because it's an equilibrium, just like what we saw previously. Keep in mind this 1 by 10 to the minus 7. This 7 might seem a little familiar, and it's going to foreshadow some things for us. So, and here they show that product constant that I was talking about. So if you have more H+, like if I introduce something to the solution that donates hydrogen ions, it will skew this equilibrium and cause there to be more H3O plus than OH minus. So if I put something in there, I can think about by adding more H plus, I'm going to make the solution more acidic by affecting the H3O plus number, raising it. And that'll cause the OH minus number to drop because this product has to stay the same. This ion product has to stay the same. This equilibrium constant is constant. So if I dump a bunch of one of these others in here, the other one will change. That kind of makes sense. If I dump a bunch of H plus in there, I'll also use up some of this OH minus. So if they're equal to each other, that's your 7. If you have more than that, more acid, then it's acidic, and if you have more base, then it's basic. Okay, so that's pretty straightforward. So they also show another way to solve for these by using the product for water, which is 1 by 10 to the minus 14, Keep all this in mind, and remember this only applies at 25 degrees. Unless stated, we'll assume that everything is at 25 degrees for water. But note that this value Kw, it increases. The dissociation of water is endothermic. With more temperature, it happens more frequently. So that's why hot acidic water could be more dangerous than cooler acidic water, just as a thought process. And this is just a pictorial description of that same idea. So how could we calculate this? Well, if we know the value for Kw is 1 by 10 to the minus 14, and they give me one concentration, which for this lemon juice is 2.5 by 10 to the minus 3 for the acid concentration, we can put that in and then divide our Kw by that and get the concentration for OH minus. And you can do this with like a Google calculator or on your calculator using the double E key, as I've shown in the demo. You can see that as a way to input these. That'll make these exponents a little easier in some cases, especially when you're dividing, so you don't have to enter like a times 10 to the or something like that. And this kind of makes sense. It should be smaller than 1 by 10 to the minus 7 because we're in an acidic solution, so that makes the concentration of the base go down. So all this kind of leads into the pH scale, right? So if I take the negative log, and this is the log base 10 of the H3O plus concentration, then I will get the pH value. And I can also get the H3O plus concentration from the pH by taking 10 to the negative of that pH value. So an acidic concentration having a concentration of 1 by 10 to the minus 2 molar of H3O plus has a pH of 2, because it's the negative of that exponent. Now that only works if the number in front is 1. If it's a different number in front, then you'll get some decimal points, because it won't be a whole power of 10. So keep that in mind. But we can generally guess about where the pH is going to be by looking at the H3O plus concentration by focusing on this exponent. So we don't have to do a whole lot of math in our heads. It's how many powers of 10, approximately. So it follows from the equation that H3O plus times OH minus is equal to 1 by 10 to the minus 14. If you take the pH plus the POH, you get 14. That's an important equation we'll be using a lot later on. Keep in mind how significant figures work for pH. Generally speaking, the number of significant figures in your number, so here 2, becomes how many sig figs after the decimal point you get in your pH. The significance properties of logs, they don't count the whole number portion of the answer. So if you had like 12 here or 2, it wouldn't matter. The number in front of the decimal point is considered exact, and then your significance affects how many decimal points you get afterward. This is because this represents a whole power of 10. So this number will get 2 significant figures. This is also really important because when you use a pH meter, even like the best pH meter in the world is only going to be able to go out like 4 to 6 digits after the decimal point. And a real pH meter that most labs would have can only do 2. So real pH meters are generally limited to about 2 digits of accuracy after the decimal point. So keep that in mind. Anything more than that can often be disregarded because it just doesn't have any effect on anything significantly measurable without extreme precision, which also means it doesn't typically have impact on chemical systems all that hugely either. This is like a power of 10. So, past 2 digits out from that power of 10, you really are not seeing much effect on the overall properties of the solution in terms of pH measurement. And again, as you probably already know, an acidic solution has a pH lower than 7, a neutral one has one equal to 7, and a basic one has one greater than 7. Now this should make a lot more sense though, because this is based directly off the exponents of the concentrations. And because it's a negative, right, these are negative exponents, the H3O plus concentration decreases as it gets smaller and smaller. That produces a number that is bigger than 7, so that's where your basic solution comes from. The neutral is equal to 7, and less than 7 is because this is a negative number. So as it increases, it becomes less negative, so it means that we need it to be less than 7. Okay. So the interesting thing about pH is it's a logarithmic system, and now we understand that it's directly related to the concentrations. Little chart here just shows household substances. So how could we calculate this pH, right? So we want to make sure we find our log button on our calculator. This is the log base 10, not the natural log, not the log E. This is the log base 10 log. Okay, so they want us to find the pH of an OH, something has an OH minus concentration of this. Now, what we could do is take the negative log of this OH minus concentration. That would give us what they call the POH, and then we could subtract it from 14. Or we could use this reciprocal process that we've been taught a little bit earlier to flip it with the KW, and then we use the negative log of that concentration to obtain the pH, 2 significant digits based on the 2 digits in the front part of the logarithm. And it's about 12, it's 11.28. You can see how there's a connection between these. It's about in the middle between 11 and 12-ish, approximately. We know it's a number between 11 and 12 because it's got a significant part over here, and it should be around that scope. So you can still use these to ballpark your answers to get a sense that it's probably around 12, just by looking at it. Similarly, okay, we take an anti-log. There'll be a 10 to some exponent on your calculator, or you can raise 10 to the negative of the pH value. You can just do that with a little caret symbol in like a Google calculator, or you can, on your calculator, you can raise it to the negative 4.5, and that will give you the value. Again, only 1 decimal point, because there's only one decimal point after the first one in the pH. Okay, and we know that it should be a number between 1 by 10 to the minus 4 and 1 by 10 to the minus 5, which it is. All right, so that will be the end of this first presentation. In the next ones, we'll go on a little bit further and talk a little bit more about acids and bases. All right, thank you very much. Bye-bye.